Good afternoon, everyone. My name is Douglas, and I come from La CNRS in Toulouse, France. And today I'm going to present to you our work about the lateral porous silicon interferometric transducer for sensing applications. So, porous silicon was a material that was accidentally discovered in the 50s by the anodization of silicon with a certain range of current density, which after some further studies, it was found to be really easy to turn its geometry characteristics, like the pore diameters, from some few nanometers to some micrometers, and the porosity from 5 to 95%. And it was found to have some impressive optical and electrical properties, which made it very useful for applications such as in photonics, and also to have a biocompatibility and a large surface area, which attract a lot of attention for microfluidic applications. Those applications are, for example, to do on-chip filtration, biosensing, electroosmotic pumps, and microreactors, which requires the use of not only porous silicon, but of porous silicon membranes. And normally in the literature, what the classical approach of fabricating porous silicon is to fabricate suspended membranes with the pores guided on a vertical manner. The problem with this approach for microfluidic devices is that it requires the use of a 3D device, because you can't apply that to a planar device. And also it difficult, for example, to do microscopic observations. So our proposal is the approach of fabricating what we call the lateral porous silicon, which is it's a porous silicon membrane with the pores fabricated on a horizontal manner. This way we can connect two microchannels in a planar microfluidic device. So the idea of our approach is to simplify the integration to microfluidic devices by enabling the monolithic integration to planar microchannels, and also enabling the real-time microscopic observation. The basis of our approach, which we already published in the Lab on Chip in 2015 and the Sensor Activated to be 2017, is to have a layer of a low resistivity p-type silicon insulated, sandwiched by two insulating layers on the bottom and the top of this membrane. And then we apply a metal electrode on only one side of the membrane. So as you can see in the simulation bottom, the console simulation, the current is guided on a horizontal way, so the pores are created also on this way. One of the fabrication processes that we have is this following process, which we start from a N-type silicon wafer, which has a higher resistivity compared to the P-type layer we are going to implant. So then we do a Bourrie implantation to achieve a highly doped P-type layer with a really low resistivity of a layer of around 4 micrometers thickness. And then we do a phosphorus implantation to get another N-type thin layer of around 100 nanometers on top of this highly doped P-type silicon layer. So this way we have the layers that are used as the insulating layers are the N-type silicon layers, while the highly doped P-type layer is where we create our porous silicon. So after that, we do a plasma etching to create the micro channels with the membrane in the middle of them. And then we deposit a layer of gold to use it as the electrode, and use wet etching to remove the gold only on the areas that to open up the one side of the membrane. And then we do the silicon anodization in a HF and ethanol medium to create the pores. And to complete the chip, we encapsulate it with a glass cover so we can do microscopic observation. This is one fabricated chip where you can see the two microchannels interconnected by the 10 micrometer thick membrane. And on the other SM pictures, you can see the pores guided on the horizontal way. And for this case, we fabricate those pores are around 20 nanometers diameter. So we already proposed some applications for our lateral porous silicon. First, the size-based separation, which we published in the same papers that I mentioned before, and also the applications considering the electrical properties of the porous silicon, which was used for charge-based separation and ion preconcentration, which were already demonstrated in the Porous Semiconductor Science and Technology Conference in 2016. And now what I'm going to show you is the use of lateral porous silicon for porous silicon-based optical interferometry. The porous silicon-based optical interferometry is based on Fabry-Pérot interferometer, which uses the characteristics of an interference wave made of two reflected waves, one reflected in the top of the sensor, in our case, the porous silicon, and the other reflected in the bottom of it. So after doing this interference, we can measure the reflectance spectra, and which by the position of the peaks, as it was demonstrated here in the SAIS 1997, you can differentiate what's the medium that you are passing inside those pores. So here, for example, they use it to differentiate the before and after the hybridization of DNA. So after measuring measuring the reflectance, we are able to get the refractive index value of the layer of, in this case, porous silicon with the filling medium. So in this case, the porous silicon with the fluid that passes through, and relate that to the position of those peaks. And after getting the refractive index of the layer with the filling, we are able to apply the Bridgman effective medium module to relate this refractive index to the refractive index of the filling medium. This way, we can know what kind of filling is passing through. So what's the motivation to use our technology in this case, to use the lateral porous silicon, is to be able to do a flow-through configuration. So for this kind of sensors, we can do both flow-through or flow-over configuration. Flow-over is when our sensor is on bottom of the channel, so the fluid passes over it. And the flow-through configuration is when the sensor is on the same level of the fluid, and the fluid passes through it. And the advantage of the flow-through configuration is first to facilitate the removal of analytes that can be trapped inside the pores. Because in the case of the flow-over configuration, we have some analytes that are trapped inside the porous silicon, and we can't remove it trivially. So when you want to do different measurements, it can be a problem. While on the flow-through configuration, you can just apply some pressure from one side to the other to push out those analytes. And the other advantage is what has already been demonstrated in analytical chemistry 2010, that flow-through sensors can offer up to 20-fold improvement in response time. This is the experimental setup that we have, where for the microfluidic experiments, where the main players here would be the Hyperion microscope with objective 36X, which is required due to the micron scale of our membrane. And the second, the Bruker outputs F tier to do the optical measurements. We did the measurements with 4 different filling mediums. First, the air, which is basically the porous silicon without any kind of fluid inside, to be used as the reference. And then we did with 3 different solvents to be able to show that our technology can work to do this kind of sensoring, water, acetone, and ethanol. And by the reflectance by the reflectance spectra here, you can already see that the redshift caused by using different fluids with different refractive index values. So after doing the measurement, we needed to analyze the data. And at first, we did use the 2 different kind of mediums to do this analysis. The first being the fitting method, which uses the relationship that I showed before between the refractive index with the position of the peaks with the refractive index of the layer to find the refractive index of the fluid. And then we also use the reflectrometric interference Fourier-transform spectroscopy, which basically we do a fast Fourier-transform on the reflective spectra to find the position of the effective optical thickness, which we can relate to refractive index of the fluid. After those two analyses, we got the following results, which has some interesting things to see here. First, that using the second method, we are able to differentiate when you had a solvent inside from air, but we are not able to differentiate between those solvents. While on the second method, we are able to differentiate water from acetone and ethanol, but not between acetone and ethanol. So we tried a different method more recently, which is the interferogram average over wavelength, which was a method proposed by Mariani in ACS Sensor 2016, which basically the idea is to obtain an interferogram from subtracting two fluids that we want to compare from a reference. So in our case, subtract acetone and ethanol from air. And then we apply absolute function to this interferogram to be able to integrate it and be able to discriminate those two solvents, even though the refractive index values of them is really close. So to conclude my presentation, we have demonstrated the capability of the lateral porous silicon to do Fabry-Pérot interferometric transduction. And we analyzed the data by three different methods, the fitting methods, the rifts, and the YAL. And by the end, we were able to identify the presence of three different solvents with three different refractive index values, providing the proof of concept that lateral porous silicon can be used as interferometric transducer. So thank you very much for your attention.